No, thank you for the introduction and good morning. So it's always good to start with a good morning. And so I will try today. So we have quite some time in the morning, so around 3 hours. And I will try to speak about polarimetric SAR interferometry. You had in the past days some notion about polarimetry, some notions about interferometry, and now it's time to put the two of them together. And we start with this image here, and you will find out what this image is during the next couple of hours. But I could also start from this image. So this is it tells you in a very schematic way what to speak about. You need, first of all, to have two acquisitions, and the two acquisitions, two SAR images, they must be acquired from a different angle of view. So you have here the one image, so you can acquire it from an airborne or a spaceborne platform, and then you need to acquire another image, but for this second image, the platform where is the radar must be in a different position so that you see the same scene from one angle and from a second angle. So, and this gives you what in interferometry you call the baseline. And then to make polarimetry, for every one of these two acquisitions, you need to transmit and receive different polarizations. This is what you do. And the idea is then you transmit your electromagnetic waves at all frequency, I would say. They will penetrate in a volume, in a natural volume. The amount of penetration depends on the frequency itself, so it depends on the wavelength. The longer the wavelength, the more you penetrate. And while you penetrate, you interact with all the different physical elements within the volume, and therefore they will scatter some radiations back, and the radiation that is scattered back will then contain information about the three-dimensional structure of this volume. And we will see this then later what it means. Three-dimensional structure for us is just the distribution of the different elements within a volume, so the 3D distribution. There could be elements of different sizes, but there could also be elements with different dielectric properties. Good. Having said this, then let's start from a simple SAR image. This is a SAR image in VV, so one polarization channel. The only you have learned that the only information that you have is basically the intensity of the backscattered radiation. So it's just brightness. So you can distinguish different scatterers which are in different pixels just because of how bright they are. And now you see here, of course, here in this image it's not difficult maybe to guess what is what. So, and then you see that, for instance, fields or bare SAR faces, they don't scatter a lot, so their brightness is low. But then you have forests, and you have also this man-made targets here in the cell, in the different pixels, that they scatter a lot more. But of course, many times to interpret what you have in an image, you need at least to know where this image was acquired. And you need to know if this is a forest, if you have ice, if you have agricultural field, whatever. But with this, you cannot make a lot. So in principle, you can maybe start to think how to use this information here to classify the different scatterers that you have, but not a lot more than this. Your problem is that you have just an amplitude, but you don't have what we call the phase. And I think you already understood that with radar, the most important part of your signal is the phase. And we will see in a moment why. Of course, you can also move from such an image, from such an acquisition, to something which is a bit more composite. So you can start now to transmit polarization. You transmit a horizontally polarized wave, and then you receive back an horizontally and vertically polarized wave, and then after you transmit a vertically polarized wave, and then you get back an horizontally and a vertically polarized wave. So what happens is that you can make all the combinations. So it's like you have, so you transmit 2 channels, you receive 2 channels, you make the combinations, and you have in total, for every location on the ground, you have 4 numbers. And these are 4 complex numbers, which are, so they have an amplitude, so they have a brightness like this, but they also have a phase. And the fact that you have a phase, you saw it yesterday, allows you to start to separate different scattering mechanisms within the same resolution cell, within the same pixel. And you are able to do this, so let's say, so what you separate is contributions which have different scattering properties. You have seen the canonical contributions, which are dihedrals, surface, volumes, or even more generically, even bound scattering, odd bound scatterings. And then from here you can start to develop different decompositions so that you can always select the scattering mechanisms that you like. But still, from here to here, so here it's only brightness, here it's brightness and phase. So you win the phase back. In particular, you win the phase difference between the different polarimetric channels. So it's always a relative phase information. But here you have it, here you have not. And the fact that you have a relative information, we said, relative phase information allows you to separate the scattering mechanism. And you see here, this is one of the most common representations, the Pauli decomposition. It's just RGB. You take the HH, VV, and HV signals, and then you images, and then you combine them in a way in which in the red channel you put the information about the dihedrals, in the blue channel you put information about surfaces, and then in the green channel you put information about dipoles, so about volumes. And you get an image of this kind. Oh, thank you, this is much better. And you have an image of this kind. You see all the now you start to distinguish the forest here. You see it, it's very green, so it's not only bright, it's also green. So you have a lot of randomly oriented dipoles. Then you have here these buildings. So buildings now, they appear purple. So you see you have a mixture there where the dihedral contributions maybe are the most relevant ones. And therefore, here before this forest and these buildings were not possible to distinguish. Now you start to distinguish. And maybe here in the forest, if you play well with your polarimetric decomposition, there you can start to distinguish between, in the same pixel, between a dihedral component and a volume component. That's the one thing. And then comes interferometry. Now, this is something that you can get with one acquisition. So in the same acquisition, you just transmit different polarimetric channels. So at once, you get this information. Interferometry, you need a second acquisition. So we said before, you need this spatial change, you need this baseline, and therefore, again, you have there a phase difference, but the phase difference is now between the first image and the second image. The fact that you have changed the position allows you to see the same point on ground from different distances. Different distances means that you have a change of distance. A change of distance means that from the same point on ground, the electromagnetic radiation, they come with a different delay because they propagate for a different path. If they come with a different delay, they give you a phase. So the phase here is related to the difference of propagation time. And therefore, you can, with interferometry, you can now start to connect. So let's say, so in an image, you can now discriminate in the range direction. You can discriminate in the azimuth direction. But now with this phase difference, you can relate the phase difference to a height. So, and now you start to get information about the third dimension. So, and therefore you can start to think now that if you, again with interferometry, maybe with a bit of models, now you can start to separate scattering contributions which are at different heights in the same cell. So, and therefore now you can put the two of them together, and you make polarimetric SAR interferometry. Polarimetric SAR interferometry is basically a way to identify different scattering mechanisms in the same resolution cell, and then to locate them in height. So it's just an increased observation space that gives you also an increased information content. And then the idea is, how do we use this observation space for extracting information and then also to get towards applications. So just maybe to see this concept in a very simple way, let's make a very simple experiment. So of course this is something that doesn't exist in nature, but it's always nice to be simple to understand the concepts. So let's say, so suppose that this is your resolution cell. In your resolution cell, you have 5 spheres and 5 dihedrals. Can be whatever, it doesn't matter. Now this is height, this is just an horizontal coordinates. And now you see that this group of dihedrals and this group of dihedrals and this group of spheres, they are at different heights within the same cell. And now what you can do, you take, for instance, HH. So you transmit HH, so you transmit horizontal, you receive horizontal. So, and therefore in HH you have both contributions. So dihedrals and sphere, they scatter the same in this contribution, in this channel. So therefore, now you have the first image of your interferometric pair. If you have the first image, therefore you have the dihedral contribution plus the sphere contribution. In the second image, you will have again a dihedral contribution plus a sphere contribution. And now you just make interferometry. You take the phase difference between the two, calculate an interferogram and you take the phase. When you take the phase, you find out that this phase corresponds to a height which is somewhere here in the middle. So you have two contributions, they sum up together. So the one is at a lower height, the second one is at a higher height. These two contributions, so the phase that you get corresponds to a height in between. This is what interferometry does. What does polarimetry? Now, with polarimetry, you can make something different. So first of all, you have to remember how these different scatterers contribute in the S matrix, so in the different polarimetric channel. And then you find out that the dihedrals, basically, they have no cross-polarized component, so they only have copolarized component, but they have a change of phase between HH and VV. So in principle, it's a change of sign, which means, of course, it's a phase difference of 180 degrees. So this means, yes. Spheres, it's different. Spheres, they have the same. So there is no change of sign, so that they scatter the same in HH and VV. So what happens now, you take for instance, the first acquisition, and now in the first acquisition, you have polarimetry, you make HH plus VV. If you make HH plus VV, so they scatter the same. So let's suppose here that, for instance, no, it doesn't matter. So they can also have different powers, but what happens is that if you make HH plus VV, because of this change of sign, so dihedrals get cancelled, so no dihedrals anymore, but only spheres survive. So this is just if you take the sum between HH and VV. What happens now if you take the difference between HH and VV? If you take the difference between HH and VV, now you take the difference, so you make this minus this, so this gets amplified, but this cancels now, because here, it's 1, minus 1 makes 0. So this means that if you take the sum of HH and VV, you select only the spheres. If you take the difference, you select only the dihedrals. This is what I was telling you before. With polarimetry, you can identify and select, now you see, the different scattering mechanism. And now if you make interferometry, what you can do? So you have two new polarimetric channels. So the one is a polarimetric channel where you have only the sphere. The second one is a polarimetric channel where you have only the dihedrals. And now you make the same for the first and the second acquisition. If you make the same for the first and the second acquisition, now what happens? If you take first acquisition, you take the sum, HH plus VV, second acquisition, HH plus VV, and then you make interferometry. So if you make interferometry, now the interferometric phase is related only to the location of the spheres. So it will give you a height which is here. The dihedrals are not there anymore. And now you make another polarization, so you take the difference. If you take the difference, HH minus VV, now the spheres are not there anymore. And if you make interferometry between the first and the second acquisition, now you have only the dihedrals. So what you get back from interferometry is the height of the dihedrals. So you see, so you select scattering contributions, the sphere and the dihedrals, and you locate them in height. And then you can also go ahead, and now you can play also with these height differences. You can do whatever you want. So, and you will see this is something that it will turn out to be very important then when we go for applications. But it's a very simple example, but tells you already how this polarimetric interferometry works. So the whole game is to be able to separate scattering mechanism. That's the thing. Now you understand the principle. Now what's the measurement? What do you measure with polarimetric interferometry? Again, coherence. I guess someone told you already, spoke to you about a coherence in the past day. I hope so. But in principle, you have the coherence is a concept which is, it crosses all these different framework. You have the polarimetric framework, the interferometric framework, and also the Polin-SAR framework. In the polarimetric framework, when you have coherence, you take just the coherence between different polarimetric channels. So let's say, so you can, and it's, in the end, you calculate it as a statistical correlation. So it's nothing different than that. And therefore, it's a measure of similarity. You can also see it this way. But this coherence in polarimetry, you just calculate the coherence between different polarimetric channels. Of course, you can also calculate the coherence between a polarimetric channel and itself. In this case, this becomes just intensity. So the phase goes away. But then if you take different polarimetric channels, then you get an amplitude and a phase. Of course, the amplitude is normalized here. So when you go to interferometry, you take the first image, second image. So suppose that here you don't have polarimetry, so just one polarimetric channel. So, and therefore here you calculate the coherence between just these two images. Now in polarimetric interferometry, you can now calculate the coherence between images of different acquisitions and of different polarimetric channels. So you can make all the possible combinations. So, and therefore it will look like this. So you see, basically it's the same concept which is common to all these three frameworks. Now the question is independent, so, or the point is that independently of the framework, the coherence also, it's something that you have to measure from data, first of all, and the coherence is, we said it's a complex number, but the absolute value of this complex number tells you also something about the accuracy of the phase. And indeed, so when you estimate this coherence from the data, you will see it today in the exercise. You will just need to implement this basic formula here, but what you have, you take the two images, you suppose that the images are already co-registered, and then once they are co-registered, you take a pixel, around this pixel you take a window, and then you see here you have all this statistical expectation, you replace the statistical expectation with just a simple average. And therefore you take here, you have all these cross products, and then you just need to average these cross products within the window. This is, in the end, is what you do. This is, of course, it's an estimate. We said before this is as a phase, so an argument and an absolute value. Being a complex number, you can represent this complex number on a complex plane. So which means you have it's a plane which is defined by an horizontal axis where here you put the real part of this complex number, and then you have an imaginary axis which is related to the imaginary part of that complex number. This is the one, but of course you can also represent it in a different way. So the absolute value of this complex number is the distance between the coherence. So the coherence will be now a point in the complex plane. You see these red dots? These are three different coherences, three different objects like this. So, and therefore the absolute value of this is the distance of this point from the center of the complex plane. The phase is the angle that tells you how much the segment which goes from the point to the center is rotated with respect to the horizontal axis. So it's an angle, so, and then therefore you always have this game. Now you see here these 3 points, and what you find out is that the ability that you have to locate these 3 points on the complex plane because of this estimation can be calculated, and for instance you can have an idea about the variance of this ability to locate the point on the complex plane. Now, for instance, you can, when it comes to the correlation coefficient is just the absolute value of the coherence. And then also in the interferometric phase, you see that both of them depends on what? Depends on the true value of coherence, and depends also on the number of looks. The number of looks is here the number of points that you use on the image to calculate this coherence. So how large is your window, essentially? So the larger the window, the better the estimate, or the larger of the coherence, the better the estimate. And therefore you find out, let's see for instance with these 3 points how it looks like. Let's take the first point. The first point is here on this circle with radius 1. So it's a coherence. Because of this normalization, the absolute value is always between 0 and 1, cannot exceed 1. The phase will be between 0 and 2 pi because it's an angle. So this means if you take a point gives you, if in 1 pixel you have coherence 1, this is the maximum coherence that you get. So this means in that case, by changing the baseline, you see basically the same scattering. And therefore, if your coherence is 1, you can just have coherence of 1 in this formula, means that the variance of the correlation coefficient, so how wrong you are in the radial direction, this variance is 0. So this means you locate perfectly this point here, this pixel in the radial direction. But it's 0 also the variance of the phase. Right? So 1 minus 1 makes 0, so the denominator you don't care anymore. So, and therefore also here you locate very well this pixel also in the angular direction. What happens now if I take the second point, for instance this one? So if I take this second point, now this, of course, now I start to increase my variance in both the radial and the angular direction. So this means here I can measure this coherence, but when I measure this coherence, I make this error in the absolute value and this error here in the phase. The problem comes for this point because its coherence is so low, is so close here to the center of the plane that you see here I make a larger variance than this point, for instance, in the radial direction, but I make a much larger error, I have a much larger error in the angular direction. So this means that your ability to measure accurately the phase thanks to this coherence concept depends on the absolute value of the coherence itself. So you always have to take this in mind. So good. Then this is also a piece of information that we will need now, because interferometry becomes particularly important when you like to extract information from volume scatterers. Now let's start with, so this is an image, it's a forest. I will speak a lot about forest, but what I'm saying now you can apply also to different volumes. But let's start with the forest. This is a forest in Finland. We take here a small patch. In this small patch you see you have fields and also you have some forest stands. So if I make polarimetry only, I can calculate the coherence between HHVV. Where your coherence is high, in the forest or in the SAR phases? In the SAR phases. And indeed in the forest it's very low. So in this case this HHVV, in principle they are independent. So where do you think, if your coherence is high in the SAR phases and low in the forest, where do you think you have a better measurement of the phase? In the SAR phase or in the forest? In the SAR phase, because your coherence is higher. Remember this plot here. So you are somewhere here. These are your coherence, these are your volumes. So basically you see here that you can measure the phase in the SAR phases more accurately than in the volumes. And this is normally what happens with polarimetry. Now if you are in your complex plane, you go back in the complex plane, SAR phases, they tend to stay here. Volumes, they are very close to the origins. And the fact that you cannot measure accurately phase in the volumes means that you have one parameter less that you can use to invert models. So in the volumes, you are back to brightness, so to amplitude. So this means that your ability to invert models and to get parameters for volumes with polarimetry is limited. So polarimetry starts to find its limits. But of course, for SAR phases, you can still do something. Then, when it comes to interferometry, so now you have here two acquisitions. You have one baseline. This is the HH coherence, so one channel. And you see here the coherence is very high. White means high coherence, close to 1. And you see it's close to 1 both for the SAR phases, but also for the forest. And you remember before, so in polarimetry, SAR phases are here, volumes are here, and now with interferometry, theoretically, we will see in a moment that this, of course, can change, but in principle, if you don't have other decorrelation mechanism, your SAR phases are on the border of your complex plane, but now you gain a lot of space for the volumes. And now with the volumes, if before you were confined around the center of the complex plane, now you start to explore it here, some larger coherences. And if you have larger coherences, you have better phase measurements, and therefore now you have a observation space which gives you some relevant and significant information for volumes. You can play many games now because the baseline is your degrees of freedom, so you can also change baseline, so you can make your planes, in this case your two airplanes, which are a bit more far away, and now when they are more far away you see that SAR phases, they have still a very high coherence, but volumes now they decrease the coherence. And we will see in a moment that this will help you to retrieve the vertical structure of the volume. But still, you play somewhere here. So, and you can now modulate your baseline so that you get a coherence that allows you an accurate phase measurement. Therefore, in this sense, interferometry and polarimetry, they complement each other in this way. So in principle, interferometry allows you to do something where polarimetry does not. Good. So this was quite a long introduction, but I think if you get this, then you get already quite a lot of meaningful information for the rest of the day. Questions? So not yet. then we can go ahead. So now we start to a bit to try to dig more in depth to try to find out, so now what are the models, how can I write my coherence, and what I can do with it. So let's start. Now you will see these slides many times today. So you have here the two platforms, so the one platform, the second platform, they have a distance, they have a baseline, you can start to make interferometry. Then we said the measurement to make interferometry is the coherence. And then how can I write this coherence? So this is what you estimate, basically. But now you can start to write models. So what do you have there? So, and therefore you can start to think, and you will find out, so the most common models they tell you, and these are, you know, the ones that are used, and they are consolidated models. You have at least 3 different contributions. You have, they multiply each other. So the one is a temporal decorrelation, it's called. The second one is a noise decorrelation. And the third one is the volume decorrelation. So let's start with the first one, temporal decorrelation. What does it tell you? Temporal decorrelation is, again, a factor. So it's by itself a coherence that tells you if what you were observing on the ground is changing in time or not. This is because you can acquire these 2 images also with a difference of time. You don't necessarily acquire them at the same time. So in this case, this is a repeat pass acquisitions. It's the case of biomass, for instance. So this means because between the one acquisition and the next one, there is some time, your volume here can change. We will see that there are different types of change. And some of them, they are more easy to be characterized. Some of them are less easy. It can change just because so the volume can be the same structurally, so the geometry, the distribution of the different elements, they are the same. Doesn't change between one acquisition and the other. But for instance, you have wind. So these elements, they are displaced in the resolution cell, and because of these displacements, you have here a decorrelation. You can try to model it, you can try to estimate it, or you can also try to have no temporal decorrelation, and in this case you must have a single pass acquisition system. So where the 2 images, they are acquired at the same time, so they see exactly the same volume and the same propagation conditions. This is the case, for instance, of tandem mix. We will see it later. But with tandem mix, you don't have any more this temporal problem. Second contribution, SNR. So it tells you how noisy is your system. So this means, let's say, so you can have many factors actually in this decorrelation factor, but it tells you how good is your system, the hardware basically, or if you like, how good are you to characterize your system, and therefore to predict when you start to lose coherence between the images. In general, it's the presence of noise. So noise is everywhere. So also we speak about electromagnetic noise, the one that is originated in the different circuit of the radar. This is the most important components. Normally this you can characterize and you can correct. Now, if you can model this and predict it, or even better if you don't have it and you can characterize this, what you are left is just the geometric decorrelation. What is the geometric decorrelation? Let's say, so this is related to your volume. So this tells you basically how much the way in which you see the volume, or let's put it like this, how much the different scatterers, which are at different heights, project differently by changing viewing geometry. So suppose with the first acquisition, you look with this angle, and therefore all the scatterers project on this viewing geometry. Now you change angle, now you look a bit steeper, and then by looking steeper, then the scatterers here, they will project differently. So it's just a geometric thing. If they project differently, you will have a decorrelation. So this introduces, if you like, a dissimilarity between the 2 images. Now the fact that this term here, the volumetric decorrelation, depends on the distribution of scatterers, now you start to understand that it's exactly this contribution to the total coherence that you need to know if you like to characterize the vertical distribution, in this case of your forest. And indeed, you can find out that this geometric decorrelation depends on the vertical reflectivity function. The vertical reflectivity function is a distribution of backscattered power. So it tells you how much backscatter you have at the different layers here between your volume, between the ground and the top of the volume. And between the volume coherence and this function here, there is this relationship, this normalized relationship, which is, for the one of you that knows it, it's a Fourier integral, it's a Fourier transform. It's a very common operator in radar. I think it's the most common one. So that's a model which is consolidated. So it just comes if you just write all the equations down. And let's see which are the other components. So this is the reflectivity function. Basically, it's the 3D distribution of the scatterers. Then what you have here, there is a phase contribution. Zeta 0 is here the ground. So basically having your volume at different heights, so just by moving this volume up and down at different heights, just changes a phase, but doesn't change anything else. And then you have a number which is called kappa zeta. Kappa zeta is the vertical wave number. And you see it here, it depends on the delta of incidence angle. So it depends on the difference of viewing angle that you have just because of the baseline in between. So the larger this difference, so the larger your baseline, the larger this delta theta, the larger this number kappa zeta. It's a real number. And it's also, you see that it changes a height to a phase. So this means that if your kappa zeta is very large, a change in height gives you a large change in phase. If your kappa zeta is small, a small change of height gives you a small change in phase. So it tells you basically how sensitive is your interferometer to changes of height. But you see, it appears here in this integral, and it's a fundamental component in all these polarimetric interferometric inversions. Then there is another number, which is this HV. HV is, in this case, your forest height. Or if you like, is it's a parameter that tells you how large is your volume. So how deep you actually penetrate into the volume and express you basically this delta height. Good, that's your fundamental equations. So, and you understand that if you start to change kappa zeta, you basically have different numbers. So the vertical reflectivity function stays the same, but you change the baseline. If you change the baseline, you change kappa zeta. If you change kappa zeta, you will have different results of this integral. And now you change many times kappa zeta. If you change many times kappa zeta, what happens? So suppose that now you start with 1 kappa zeta. This 1 kappa zeta gives you a point. So you can now you can plot the coherence, the interferometric coherence, as a function of kappa zeta, as a function of the baseline. So you have one baseline, every baseline gives you 1 point here. Now you take a second baseline. You take the second baseline, suppose that it's longer, it gives you a different points. And now you take a third baseline, it gives you a different point again. So this is what you measure. You actually measure this number, you measure these coherences, but now every time you change baseline. So the baseline is your degree of freedom, you change baseline, you have a new measurements of coherence. Now you collect many coherences. If you collect many coherences, you can basically draw this behavior here. If you draw this behavior, you know that between the behavior of the coherences with kappa zeta, you can put it in this Fourier integral, and you get back what? The vertical reflectivity function.
By baseline, you mean the height of the satellite, or you mean the distance between satellites that are more or less of the same height?
Here, so precisely what I mean is the projection of the position of the two satellites in the direction orthogonal to range. That's a bit a complicated way. This is what the baseline is. But in general, its baseline is for me here the distance. It could also be the distance between the two satellites. It's not important. The important is that it's different from 0 when you project it in the direction perpendicular to the line of sight. But it's just a change of position, and this gives you a baseline. So of course it would be different. Now let me maybe come back. Maybe let me come back here. It would be problematic if you change your baseline in this direction along range. Because if you change baseline along range, then you have kappa zeta equals 0. So in principle, this means you always make just the same measurement. So you have no phase difference between them. So you need somehow to have something of this kind. In many cases, they are horizontal. In some cases, they can be also vertical. This depends how can you fly. So it depends on your satellites, it depends on your airplane, it depends on these configurations here. Good. Sure. Mm-hmm.
Over the sea, there is a lot of changes in the condition, so we
Sure.
say that it is never the same.
Mm-hmm.
So why in the previous
This is for recording, sorry.
why in the previous image the coherence over the sea is high? Of course, it depends on the resolution of the SAR image, but I expect for a coherence that is low. Maybe I misunderstood.
Which image? So
Yeah.
no, there is no sea. This is just a surface. There are fields.
Okay, no, not sea.
So no, it's not sea. It's not water. If it was water, you are perfectly right. The coherence would have been 0.
Okay.
So normally it's 0. Yes. Correct.
Hi, sorry. Can you explain a little bit more about vertical reflectivity function? It is dependent on the forest type, or so how we
Yes.
can estimate it for different forest type? We just pick a simpler function, or is there like better approximation? Because I believe this is what gives an error in the volumetric coherence in the end. If this vertical reflectivity function is too approximated, it's like if it's wrong to the forest type, how we can minimize this error?
I will speak about it later, but you need to wait a couple of hours for it. No, but yes, I have some slides about it, about how to reconstruct the function. For the moment, let's say, just to give you maybe an idea. So you can parameterize. So you say this function depends on certain parameters. One of them is for sure height here. Because this height here, you change this height, you have a different coherence for the same shape, for instance. But you can also have parameters that describe the shape. Or you can also say, I don't like to have parameters. I try to estimate the shape as parameter-free as possible. But I will come back to this point later. So tomography is, for instance, a way to estimate this vertical reflectivity function and to try to make the most, basically, what I was telling you here. This is what tomography does. So you collect many measurements of coherences. You have this curve here, or you try to reconstruct this curve here, and from this, with just a Fourier transform, you invert this equation here, and you get your reflectivities with an error, of course. But this, I will speak later a bit more about this, how to get reflectivity. Other questions? Yes.
You said that at the end we can estimate the signal to noise ratio and remove it from the coherence estimation.
Yes.
But is it something that is good enough and is it something that is evaluated for the whole image or for the single pixels you have to evaluate, estimate the signal to noise ratio and remove it pixel wise?
let's say, so in principle, you have to, the signal to noise ratio depends on the backscatter. So how much your scene is backscattering at that point, because it's the ratio between the signal power and the noise power. So what you actually need is, so you need the backscatter, so but this you have it because you measure, and you need a characterization of the noise. And the noise is normally done pixel by pixel. Now, how good is this characterization? This depends on your platform. So normally all the most recent platforms, Airborne and Spaceborne, they have a way to get signal to noise, to get these noise patterns. So this means they are normally annotated, and then you can calculate the noise pattern, you calculate the signal to noise ratio. There are equations that give you the gamma SNR. That's the one way. The other way is, I'm not sure if you saw it yesterday, but also to use polarimetry. You can take HV and VH, and therefore if you have some reflection symmetry from HV and VH, you can, so in principle this means that the scattering is the same between the two channels, but it's the noise that is different. So if you calculate the coherence between HV and VH, since you have the same scattering, the coherence that you get, it's basically already your gamma SNR. You have these two ways. They are normally good enough, and then sometimes you need a bit to fix the parameters, but it's normally fine. But this we will see today in the exercise what this means, having a wrong guess about this system decorrelation. Other questions?
Yeah, I have one more small question about, there's like two exponents in all these equations.
Yes.
And both have a kappa z factor. Is it the same in the equations, or is one for them just for the baseline? Or, yeah, there I was a bit confused.
Where precisely?
Like just in these equations, you just said there's
No,
like
here you change it. You change it.
Yeah, and the one on the left side?
This basically is generic. So basically,
no, I mean in the prefactor, like this, before the integrals, there's also an exponent too.
No, this is wrong. This should change. This is capacita 1. Yes, of course.
Okay.
This is capacita 2. No, it's 3. And this is the capacita 2. No, this is a typo. Thank you.
Okay.
Yes, correct. But no, every relationship here, whatever you have in this equation, it's everything calculated always for that capacita. So, other questions? So, then we try to go ahead. Now you know all the basic relationship. The question is maybe to give you some examples of this relationship here. So, if I give you a reflectivity profile, how does the coherence look like? Let's take a surface. If I take a surface, I think my reflectivity will be concentrated to the height where this surface is. So you have a field, this field is at a certain height, and therefore the reflectivity is a Dirac delta at that height. What's the Fourier transform of this? If you like to estimate to get the coherence, you need to calculate the Fourier transform of this delta Dirac. You have it here. In principle, you need to calculate this equation, and we take the absolute value. So if it's a Dirac delta, you take the absolute, you calculate this integral, you take the absolute value, and what do you get as a function of kappa zeta, as a function of the baseline? Someone that knows it? Then if you don't know it, I tell you, coherence 1 everywhere. So it's a Dirac delta, there is no reason for it to decorrelate with kappa zeta. So it's a constant. So, and it's a constantly equal to 1. So the maximum coherence that you can get. And now you take a volume. Let's suppose you have this volume with this height. Same story, you take this box. You put this box in the equation, you get the coherence. So maybe I don't care if you know the formula or not, but just one important point is, what do you get? You get something that decorrelates, you get something that stays constant. What's happening here? Exponential. Sorry? It's exponential. No, it's not an exponential. Or maybe it could also be an exponential, but with some characteristics. A different opinion. It should go down. So now, for instance, for this volume, this is a tall volume, and you see it goes down. You take 3 different capacitors, it goes down. Maybe at some point it comes up. Depends on how large are the capacitors that you get. Let's take now a different forest end, but which has a different height. So in this case, you have a smaller height. So this is a case which is in between this case here and this case here. And you see here the coherence goes down, but it's lower. So this means that, for instance, you can have the same capacitor, and then for this same capacitor, now you try to make the, so this is something that you don't know, but this is something that you know. So you have the same capacitor. You measure the coherence, and therefore if your coherence is equal to 1, then maybe you are in somewhere in this case. But if your coherence starts to decrease, then this means that you have a volume. So this volume has a certain height. Now, of course, to be able to associate this coherence here that you measure to a height, then you need to know this behavior here. So there you need a model. So you need that someone tells you what's the reflectivity. If you know what's the reflectivity, or at least the shape of this reflectivity, then you can associate what you measure here to, for instance, a height. But you see that already knowing the absolute value of the coherence, you can start to understand something about your scene, and you can start to understand where you have larger volumes or where you have shorter volumes, or maybe even where you have surfaces. Let's make an example. So P-band, Sweden, Remnistorp, forest site. So this is just an amplitude image in HH. Now interferometry, we take a relatively small spatial baseline. So the baseline is small, and you see in many cases the coherence, you calculate the coherence, you take the absolute value. In many cases this coherence is white, means coherence equal to 1. Coherence equal to 1 means in many places, of course there are places here, take this is very much close to 1, somewhere else starts already to go away from 1. So and therefore you start to think, this is maybe a surface, somewhere else maybe I have some volume. Let's increase the baseline. Now this is a baseline that tells you something more. Now you see that the contrast between the surfaces, somewhere here, and the volumes and forests now starts to be stronger. So now here you start to have a better idea. Now you make your baseline even larger, and now you see that the contrast increases even more, and so on. You see now you increase the baseline. When you increase the baseline, you have exactly the behavior. You know, you remember the surface has a high coherence, and this coherence stays pretty constant, while for volumes the coherence decreases. Now let's take some points. So let's take this. This is indeed a surface. This is what we said. The coherence stays equal to 1. Now this is a volume somewhere here. You have, of course, some small surfaces, but then here in this patch you also have some trees, and then where you have the trees, so your forest volume, the coherence is going down. It's going down with a certain slope, with a certain pace. Now you take this one here. Now here you start to see that here it's already a bit darker than this, and then it becomes darker and dark faster. So can you tell me where is the higher forest? Here or here? So the purple or the green? Where is your forest taller? The green, because the coherence is going down pretty faster. And then you see already just by looking at coherence, the absolute value of coherence, and here now you don't have a model. At the moment nobody told you what's the reflectivity, but of course you have many baselines, you have 3, 4 baselines, so you can reconstruct this behavior of coherence, and therefore you get an idea, for instance, at least where is your forest taller. Okay, then we move ahead. And this is what, it's surprisingly, this is something that we saw also even on X-band. So that's a global coherence image obtained from tandem X coherences. So X-band, you expect that it doesn't penetrate. Now you calculate this coherence. Can you tell me where the coherence goes down? So this is just simple geography. Where does the coherence goes down? The desert, but this is a different story. I tell you later. Somewhere else. Forest. Someone says forest. So indeed, in the Amazon, it's going down. Central Africa is going down. Siberia is going down. Ice, Greenland, look how it looks in Greenland. Indeed, wherever you have a volume, because you penetrate even at X-band, this, if you like, was not expected before the mission, but then with the data, data always speak, and they tell you the truth. And indeed, you see here that where you have forest and ice, this sort of volumes, your coherence goes down, means you penetrate, and you actually see a volume even at X-band. Desert, someone was saying desert. Desert is a different story. So what do you have in the coherence? Which are the three contributions? So one is the volume. The second one is the noise. The third one is time. Tandem X is true acquisition at the same time. Do you have temporal decorrelation? No. So there is no time here. In any of these points, you have a temporal decorrelation. Then volume. In the desert, can you have volume decorrelation? Maybe, but it's X-band, and you need a very, very dry volume. Maybe there is something, but at X-band, I can tell you it was not really proved. With biomass, you will see it, of course. At P-band, you will start to penetrate and see something more. But then, if maybe it's not volume, it's not time, then the third one is noise. What you see here is noise, basically. The reason for this is that, indeed, because you penetrate, but at some point, the extinction is so high that nothing comes back to you. So you have no backscattering. Everything that you have in the data is noise, or at least a big portion of contribution that you have on the data is noise. So that's why here it's black. But anyway, you see that wherever you look, wherever you have a volume, even with a shorter wavelength, you have a decorrelation, and therefore you can start to get properties of this volume. So then, how do we proceed? So we were seeing what's the information content of the absolute value of the coherence. What about the phase? The phase, we said at the very beginning, the phase is related to a height. But of course, if you have a surface, it's easy. It's the height of the surface. You have nothing else. You just scatter just at that height. What if you have a volume? If you have a volume, you have a reflectivity function. This reflectivity function is extended between a ground and between a top. So therefore, in this case, what you get in the phase is just, we call it the center of mass of the reflectivity function. It's a point which is there in between in this, if it's a forest, between the ground and the top. But in general, it's somewhere within the volume, and the height of it depends on how the reflectivity is distributed at the different heights. So this means, but still, it tells you something about this distribution, if you like. Because if you know, for instance, where your ground is, suppose that someone tell you the height of the ground. It's a forest, you know where the ground is, and then you measure the phase, the phase. You convert this phase to height. How do you convert phase to height? With the capacita. So you take the phase, you divide by capacita, you get a height. And therefore, if this height here it's closer to the ground, then you start to think that maybe all your, or a big part of your scattering contributions are indeed closer to the ground. But if your phase is close to the top, then you start to think that your scattering contributions are mostly located to the top. And this is something that has to do, on the one hand, with penetration, but on the other hand, also on the characteristic of your volume. For instance, if it's a forest, it makes a difference if you have a closed canopy or an open canopy, or maybe for the same canopy if the forest is drier or if it's wetter, or there is more water inside or less water. So you have all these considerations, but in principle it tells you something indeed about this reflectivity function. So with the absolute value you get the width, with the phase you get a point which is in between. And you start to understand how is this function, what's the skewness of this function, for instance. Then, so let's start. This is basically how reflectivity functions look like. So this is a forest south of Germany. This was an airborne acquisition, and then we applied tomography, and we got these profiles. I can tell you this is something which is at the ground. You see, you have quite a strong ground backscattering. You have here also scattering from the forest canopy. That's a rather close and homogeneous canopy. Then something maybe you have opening. You don't know if this is indeed because you have an opening in the canopy or because here the forest is drier than here. But in general, you see you have also different shapes of this reflectivity, depends on how your forest looks like. Then you can also change frequency. So reflectivity depends on frequency. You change frequency, you have a different reflectivity. Why? Because with the frequency, you are sensitive to different scatterers of different size, and you also have different attenuation. You change frequency, so now you have a case in which you see a lot of ground. So it's the same, these are the same points on ground. So you see a lot of ground here, very, very strong. Somewhere you see also a bit of forest volume, something here, but in most of the case it's almost transparent. But now here it becomes very, very strong. Then you change frequency again, and you see that, for instance, here you see you have the opposite of this. You see that you have a lot of scattering from the top and quite some reduced scattering from the ground. It's not zero, there is still something, but it's very reduced. So now, first question, phase center height. Where is, so you take, let's take this as a reference. So suppose here you measure a phase center height. Where will be your phase center height? So your interferometric phase higher, here or here? So same forest. The top one, the phase center is higher. Why?
Because it's surface.
But here, where will be your phase center? Let's say it like this. Where will be here your interferometric phase center? So your interferometric phase will be somewhere close to here, somewhere close to the ground, or in the middle. In the middle. And here, for instance, here you have, someone said correctly that here there is a lot of surface. So where does the interferometric phase go? Close to the ground. So it becomes lower. And here? Higher. So therefore you change frequency, you have a different phase center. Now, which is P band, which is X band, which is L band?
X band is the yellow one.
X is this. Why?
Because its reflectivity is directly at the canopy.
I agree. Now, which is P and which is L? Top one is P, and the one in the middle is L. So I agree. Indeed, the one in the top is P band, the one in the middle is L band. You see at P band. Now this is a particular case, it's a temperate forest. In tropical forest, it's not like this. So in tropical forest, you have a lot of scattering also from the canopy. But in general, you see that in this temperate forest with L band, you have a balanced scattering between the ground and then the volume. At P band, you still have a dominance of the ground, and at X band, you have a dominance of the canopy, which, however, doesn't mean that you don't penetrate. Somewhere you penetrate. You have some scattering from the ground. Weak, but it's there. And still staying at X-band, now this is just to make you an example, how can I, so the phase center is not only locating, of course you can locate your scattering height, but now if you start to observe it at a larger scale, it tells you something about your forest structure. So this is a forest in Bolivia. And you see there is also some topography. Of course, these are all the features of topography. Now, you see here, you have some patterns, some lines. And this is X-band, tandem X, no temporal decorrelation, the system is fine, no problems. Therefore, at the beginning, we started to think maybe, it's broken, something is happening, or we had a problem in the processing. So now if you take a zoom, do you see what's this? Someone can imagine what's this? You see, it's very geometric. This is deforestation. These are deforestation patterns. And the funny thing is that now you have X-band, you have high resolution, and even if you don't know where your ground is, but just by looking at the variability of the interferometric phase, you already start to get a clue about structure. That's the power of interferometry, and the fact also that you don't penetrate, so you are able to see this height variation. But this is just a simple example to tell you that in principle you have information also where you think that you don't have. Anyway, let's go ahead now. Enough for the fun. We go back a bit of mathematics. So this is a slide, so just to tell you in principle what Pauline SAR does. So we said at the beginning, now this connects with the very introductory slides where you remember we were taking for what we were doing, we were taking so you have the polarimetric acquisitions, so at the two ends of your baseline, and then you start to combine the different polarimetric channels so that you are able to see scattering mechanisms, different scattering contributions with different characteristics. And what you see here is just an algebraic generalization of this concept. So you have the two acquisition, you have image one, gives you a S matrix, so in principle you have all the different HH, HV, VH, VV for the first acquisition. You have the same for the second acquisition. Now what you can do, you can also make them a vector if you like to be precise mathematically. You have the first vector, the second vector. Now you can start to change polarization. To change polarization, you do it by playing with this W vector here. So this is, for instance, it's a quad-pole acquisition. From the quad-pole acquisition, from the S matrix, you build up a three-dimensional vector. And therefore, if you like to combine the different polarizations, you need three coefficients. And you make it with this vector W, and W is a vector that helps you to select a polarization state. So it's arbitrary. You can select whatever you like. For instance, you have here an example. So from the scattering matrix, where you have the lexicographic basis, now you go to the Pauli basis, and now if you like to have from this vector here, you like to have, for instance, the first component, you just need to have a W vector which has 1 in the first position and 0 elsewhere. And then in the end you get basically your first Pauli component. This is what you do. You can also get from here, you can also get HH. To get HH, you just need to take the sum of the first two and then to put a 0 here, and this is what you do. You see, you have the same coefficients in your W vector and a 0 after, and therefore when you multiply this W vector times this K1 vector, so these are your data, these are the coefficients of the combination, and therefore from your data you get HH. So it's purely, you see, it's purely, how to say, something mathematic, but allows you to formalize this concept of selecting polarization. And now you can play. You can, how to say, you can have the one vector, so this one vector W for the first and the second acquisition. Then you get new images. In principle, you can also have, in the most general case, you can also have different W vectors. You don't need to have one W vector for the first acquisition and a W vector for the second acquisition. They could be the same, they could be different, but in the end, the concept is that from all polarizations of the first image and all polarization of the second image, you make a new image. So it's just a normal SAR image Renz azimuth, and then you can calculate the coherence, and you have an interferogram. So a coherence with the absolute value in phase. Very simple. And now the question is, after you do this, how things change. Let's say so, you can now ask yourself, what are good values for this W vector? Can I optimize them in one way? And of course, you like maybe to maximize the coherence. So you start from 3 polarization, all of them, they have different coherences, that you like to put them together so that you maximize the coherence. Do you have in mind an application for doing this? Why you like to maximize the coherence? Slide number 3 or 4, something like this. If you maximize the coherence, you reduce the variance of the phase measurement. So you like to make a DEM, you like to have an accurate DEM, you use polarization to maximize coherence so that the accuracy of your DEM is higher. This is, for instance, one possibility. And you see here with data what happens. Again, data always speaks. So we start from the same forest. We fix a baseline. And this is the HH coherence. And now you make this game, you take HH, VV, HV, you optimize polarization, and you find the W vector that gives you the maximum coherence. That's the result. And you see that you optimize your coherence, you increase your coherence everywhere, in the SAR phases, but also in the volume. Of course, if you find the maximum coherence automatically, you also, because of all the optimization involved, you find also the minimum coherence. And you see now that, so this is what you have. Now, how to do this? There are papers in the literature. This is something, it ends up everything to a eigenvalue, eigenvector decomposition. So it's something that you can write in closed form, you can implement, so it's nothing really, there is no particular optimization involved. So, but the important point is that now, if you can, we said, so we start from the polarization, we combine the polarization, we make new images, and we calculate the coherence. You can also think about, for instance, optimizing the polarization so that you change the reflectivity function. You have a new coherence. If you have a new coherence, you change the absolute value of the coherence, but also the phase. For instance, you may have a W, so you start from some W vector, and now you change the W vector so that you start to cancel the ground in your scattering, and you end up only with the volume. If here, for instance, of course, for forest. Or you can also make the opposite. You cancel the volume, and you end up with the ground. So, and this is a possible direction where you can start to use your Pauling-SAR optimization and also this concept of selecting and optimizing scattering contributions with polarimetry. You see, normally, of course, then in reality, you never cancel completely the ground or cancel completely the volume, but you minimize them in a way that you can, of course, simplify a lot the inversion problems. And this is something that we will see later. And now you see, for instance, that you change also, when you make an optimization of this kind, you change what? You may change the absolute value of the coherence, but in a more sensitive way, you change the interferometric phase of the coherence. Because if this is the one coherence where you start, which has a certain interferometric phase, a certain phase center above the ground, now here you move the phase center down, and here you move this phase center up. So therefore, here you understand that you try to, by changing the vector W, so the polarization, you try also to move your coherence in a radial direction in a complex plane. So, but this, we will see it later, what it means, but maybe again data. So let's try to apply this concept here of changing polarization to tomographic data. So we start from a tomographic acquisition. This is the very first tomographic experiment. So we speak about L-band. There are many, many tracks, many, many images. And so it's still in the 90s, end of the 90s. You also here have the reference. And so there was in the images, this is one of the most iconic results from this experiment. So they were, say, having tomographic profiles for different scatterers, for instance, from a forest. You see here in the forest you have, so green returns, these are Pauli composite. So you make tomographic profile in the different polarization and then you combine them as they were Pauli, as they were, you know, normal backscatter image in a Pauli combination. And therefore you see here on the forest you have dihedral contribution at the ground, the Pauli is red, and then you have a lot of volume here in the canopy. And then here also at the building you have a lot of dihedral and surface at the top, at the roof. Then you have some dihedrals here at the cars, some double bounces between the car and the ground. And then you have a corner reflector here that appears blue in the Pauli. So if it's blue in the Pauli, it's a dihedral or a trihedral? Someone that likes to guess. Dihedral means 2 bounces, trihedral means 3 bounces. Trihedral, if it was a trihedral, so yes, exactly, correct, because it's blue. So the Pauli, this Pauli component here, HH plus VV, it's normally maximized when you have an odd number of scattering, of bounces, while it becomes red when you have an even number of bounces. Indeed, this was a trihedral reflector. Anyway, so let's take some points. Tomographic profile in different points at different, so say, let's say here in a surface, a different polarization. So you see here you have on top HH, VV, HV, now, and now here on the bottom you have, this is HH plus VV, HH minus VV, and twice HV. So it's a surface. The only scattering contribution is located at the ground. There are no other scattering contribution. Everything else, this is basically side lobes of your tomographic profile. It's ghost, so, but they are small enough so that you don't confuse them with the real scattering that's here at the surface. So, and you see the surface looks the same in all channels. Interestingly, you also have some scattering in HV. So now for all the models tell you that surfaces, they don't scatter in HV. But actually, in real data, you always find a different thing. This can be for a number of effects, but just that if you make a tomographic profile, even of a surface, you will find some scattering also in HV. Very reduced. You see here, for instance, if you take HH plus VV, where you have where your surface should be maximized, it's between 0 and 5 dBs. And now here it's already below minus 5 dB, so it's very attenuated, but still it's there. What happens now in a forest? In a forest we take, so if you compare HH and VV, so this is a stand which is between 15 and 20 meters tall, and in this stand of course you penetrate, so you have a ground scattering between HH and VV, so you see the ground in the 2 channels. But in VV it's more attenuated. Can you tell me why? What's the difference between HH and VV in terms of information content at the ground in a forest? Double bounce effect, exactly, correct. because this dihedral component, which your electromagnetic wave bounces on the tree trunks, then get bounced on the ground, and then comes back to the radar. So the double bounce component is normally stronger in HH and weaker in VV. So this means if you move from HH in VV, you still have some ground scattering remaining, because you may always have some direct surface return, but the dihedral returns, they are attenuated. That's why here in HH is stronger than in VV. And now in HV, then it becomes very, very attenuated. Of course, you can play now with polarizations, and now just already by employing a Pauli decomposition, and then you take the HH minus VV. If you have dihedrals in HH, or theoretical dihedrals in HH minus VV, they are there. And indeed, you see now in HH minus VV, the scattering here is stronger than even in HH at the ground. So this is, of course, this is something that you would expect. But the contrast between the ground and the volume in HH minus VV, it's much stronger than in all the other polarization channels. And this is just because you focus now on the ground more because of polarimetry. You amplify the ground rather than the volume. But you see, you change polarization channel, you change the profile, so this means you change the contrast between your ground and the volume. So this is what you do. And therefore, this justifies the idea of, for instance, using this optimization of this W vector to try to cancel the one and amplify the other. Of course, you can take a different stand. Different stands, of course, they have different forest, so therefore they have different attenuation, but the message is still there. So then, at this point, so we can also somehow formalize this concept. So in principle, what you can do, you can now, so we said you take the one coherence, then you calculate this coherence for different polarization states, so for different W vectors. What you find out is that now you start to change. You can also make an experiment where you randomly select this W vector. And whenever you change W vector, you find a coherence, and then you plot this coherence on the complex plane. And you will find out that all the coherence, they stay, when you change then polarization in this linear way, so all these coherence, they are in one region in the complex vector, which is called the coherence region. So it's a region which has a boundary. So you can also then write all the equations to get this boundary. So again, you end up with some eigenvalue, eigenvector decompositions. And normally they are regular, these boundaries. Now here they are depicted as an ellipse, but they are not ellipses many times. So they have a bit of different shape, but in general they tend to be many times more elongated in one direction than in the other. And yes, all the coherence are here. And now you can start, we say, to optimize. So, and therefore when you optimize to try to look for the coherences with minimum and maximum absolute value, basically you tend to take points in the coherence region which have the largest distance in the radial direction. So this is what happens. You can also maximize for this angular direction, so what we said before, and therefore you take the 2 points of the coherence region which have maximum separation in phase, so in the angular direction. Here we said you maximize the coherence, for instance, because you like to have a better DM, and here you maximize this phase separation. Maximizing a phase separation means maximizing the difference between the underlying reflectivity functions, which means, as a first order interpretation, to cancel scattering contributions or to attenuate scattering contribution and to amplify others. So typical shapes are radial shapes. Radial shapes is a surface. So in principle, when you optimize a surface, you cannot change vertical reflectivity function. A surface is somewhere which is well located, so you cannot change its interferometric phase. There is no other scattering. So what you can change, you can just optimize its absolute value. Then by optimizing its absolute value, then in principle you optimize against noise. So you try to find the polarization with the maximum ground to volume, with the maximum signal to noise ratio. Then in forest, what we said before, so you try to, by changing point in the coherence region and by optimizing all this W vector, you in principle try to select scatterers which are at different heights. And then you have a coherence region, which is, this is the most terrible one, the coherence region which is a point. When the coherence, you have your data, you calculate this coherence region and you find a point, that's the case in which polarimetry doesn't help you anymore. There you are lost. And this is the case of a random volume. If you have a random volume of scatterers, then at this point, you are left only with interferometry. There is no polarimetry anymore. So this means if you like to get information from your volume, about your volume, because you like to invert models, then you have to resort to what? What can you change? What is your degree of freedom in interferometry? The baseline. That's the 1 degree of freedom. So this means at this point you start to move your point. You can still represent all the points at the different baseline in the complex plane, so you get other points. Or if you like to cancel scattering mechanisms or scattering contributions, what can you do? A baseline sees, if you change a baseline here, you have the same reflectivity, or at least you think you have the same reflectivity. But now, if you like to change reflectivity, what do you change? You change the frequency, exactly. So you move from, from an L band to a P band or to an X band, and therefore you go up and down in height, and then in this way you attenuate the scattering, different scattering contributions. Good. Now, maybe before questions, this was an example. So this is tandem X. Now, tandem X in its basic acquisition mode, it's single polarimetric, HH, but somewhere can also, and for experimental purposes, there are also dual pole and even quad pole acquisitions. This is an example of a dual pole acquisition. So, and you have here a optimized coherence. Now, when you have only 2 polarizations, the coherence region becomes an ellipse. That's your only case in which you are sure that the coherence region is an ellipse. But the experiment was, so I have X band, I think I don't penetrate, but this is already, how to say, so the data already say it's not true. Now I like to see, so how much, even if I penetrate, but I don't penetrate too much, how much can I change? The polarization can change reflectivity. Do I still get a difference of phase center height when I start to change the polarizations? This was the experiment that was done here. What we did was indeed to optimize, to find the W vector that gives you polarization channel with the maximum interferometric phase difference, so with the maximum height difference. And this is what you see. Now, here the contrast is not too much, but you will see that wherever you have here this decorrelation, this volume decorrelation here, then basically there you have a phase difference. So this means these volumes, they are not too thick, so you still have some penetration, you still see some ground, and therefore because of this, you are still able somehow to select a ground or to select a volume. So even at X band, even in the reduced polarization condition, still polarimetry gives you an observation space which is valid. So, and the same concept, of course, we started with forest. but the same concept applies, I said many times, they apply to agriculture and to ice. So whenever you have a volume, and depending on of course, depending on the environment, you have different applications. So you start, for instance, in forest. I think forest height is the most demonstrated applications of Pauline SAR in forest. It's the one which has been very well documented. We know performance, we know what to expect from it. In agriculture, of course, you have, so still in forest, so getting vertical structure is another important application of Pauline SAR. And then from there, if you have height and structure, you can think also how to use the two of them to get biomass. For agriculture, the fact that you are able to separate scattering mechanisms with polarimetry gives you the chance to separate the ground from the volume and to address moisture estimation at the ground and at the volume. So this is something that's still in progress. So the understanding, it's growing but still limited. And of course, agricultural volumes, they are always quite challenging. When it comes to ice, so for ice, there is you can still apply Pauline SAR to get structure still. So where are all the different ice layers? You can get one parameter which is normally looked for is the penetration depth, and this many times to correct DEMs, but not only. You like to know, for instance, how thick is your snow layer, and you like also to get snow water equivalent. So it's a number of applications that you can address. With which sensors? So where is Pauline SAR? Pauline SAR is, of course, now in many airborne platforms. So DLR's FSAR acquires full pole in different frequency from P band up to X band. But other, of course, you have also other platforms that gives you the same. When it comes to spaceborne platform, now here it starts to be where is polarimetry? You have in the ALOS systems from ALOS 2 up to ALOS 4, even if quad pole acquisitions are not systematic, but still you can get something there. Of course, in RadarSat, you have it in Sentinel. Sentinel is only dual pole and has this funny configuration where you have one co-pole channel and one cross-pole channel, HHHV or VV, VH. Still, it's, for many reasons you can find out this is not maybe the most, how to say, it's not maybe the most informative configuration, but still you can start to do something. You have polarimetry in SAOCOM. In TandemX, not always, but TandemX I think you appreciate a lot more for interferometry. It's the only system that gives you interferometry systematic. Even if TandemX was not designed to invert parameters in volumes, TandemX was designed only to have to get a DM of the surface, but it proved also to have a lot of information content also for volumes. For forest, agriculture, and ice, you have a lot there. In all the other cases, many times baselines, you don't have them. So they are platforms which are designed to be zero baseline because they focus on different applications many times for the formations. And there you like to always to be sensitive to the formations rather than, so to movements rather than to volumes. Of course, a game changer is biomass. Biomass is the only mission today that provides you polarimetric, interferometric, and tomographic data, systematic. And in principle, what you see this week, all the techniques that you have seen this week, you can apply them one-to-one to biomass data. And biomass data are free, so the only way for you to just to get downloaded and used. You can also have, but the future, how does the future looks like? Well, NISAR was launched in this summer. It can have some polarimetric, it has some polarimetric capabilities. Again, what you have here are the baselines, close to zero baselines. But of course, there is Roselle. Roselle is similar to NISAR in terms of concept. there are also options which are being evaluated so that you have also a baseline. So this could be through companion satellites especially. And then Tandem-L was, it stayed as a mission proposal, but by itself it was something that, so single pass interferometry with quad pole acquisitions, it tells you that it's something that can be realized. Good, so now maybe before the break, questions from you? Unclear points?
There was plots of different frequencies of vertical structures when we tried to determine the phase center.
Yes, this exercise
There
that
was
we...
one point that you mentioned that maybe there was on the top of canopy the hole, or there was a dry. Can you explain why it can be dry as well? I didn't quite get why it can be.
It could be somehow, maybe because it could be dry, so let's say so it could be this a stand where you then, your water content is lower for some reason, just because it's a bit more open. I don't know, physiologically what could be. But of course, what is important to know is that how much a forest volume scatters depends a lot on how much water you have inside and on top. So we will see later examples of the same forest and with data acquired before and after a rainfall, and you see the profile, they can change dramatically.
Okay, thank you.
Even because of that.
Also, the next slide about deforestation. Can you explain why the patterns look like this?
This is because when deforestation is always geometric, so they start and they go ahead. Now here, it's I think it's also maybe for some also to build up some plantations. This I don't know. So, but in general, it's if you take data where you have some deforestation, you always have these geometric patterns, many times.
Thank you.
Of course, this is a bit of a particular case. You see, you have basically clearing, and then you have one row of trees which is left there. You see this just because of tandem mix of high resolution and limited penetration.
So about that image,
yes,
that's the canopy, right? That we see.
Exactly. What you see here, it's a phase center which is between the ground and the canopy. So it's a X-band EM, and you see here especially it's a part of forest which is untouched, and you see that your phase suddenly becomes very, very rough. So you have a lot of variation, spatial variation, and that's indeed because of the characteristics of the canopy. So somehow in some point you penetrate a bit more, some point you penetrate a bit less, so your phase starts to move up and down.
Second question, did you relate it to a p-band or to look at the DM of that same image to see if there is?
Not here, but in some other test sites we did also these exercises. So we took the tandem mix interferometric phase and we plotted it. So before alone, so we calculated the phase variations. And then we tried to relay this phase variation to height variations. And this is an indicator of structure, basically, how open is your canopy. And this is something that it's indeed there. So it's the variation of the tandem mix interferometric phase changes with canopy structure, with this sort of horizontal canopy structure. And then we did the same exercise, of course, after removing a ground topography. And there what you see is that in this evaluation of the variability of the canopy, of this canopy height, now you have less ambiguities. So this I can show you. Then when it comes to P-band, P-band it's a bit of a different story, and in particular for the biomass data. So in the biomass data you also have the resolution, which is much lower. So this canopy height variability, because of this, they become a bit more difficult to be seen. But at P-band you have I think the observation space is still rich because you penetrate. Therefore, if you penetrate, you are sensitive then to structural variations which are in the vertical dimension, and therefore, so you see, you have a different information content. So now we start to invert parameters. So you know now what to do. You have polarimetry, you have interferometry, you know what to optimize, how to optimize, and now you have measurements and you like to invert for parameters. So let's say so, same configurations, you have a forest below. As I said, I will speak a lot about forests, but this concept you can apply them also somewhere else. But in general, so you have your interferometric acquisition, a forest below. What you measure in whatever polarization you have or you optimize is an interferometric coherence. This interferometric coherence depends, you factorize in different contributions. You like, if you have a system decorrelation, you like to calculate and compensate. If you have temporal decorrelation, you like to estimate it, or even better, you don't like to have it, but this you need to change radar. And what you like to have is volume decorrelation, because if you have volume decorrelation, this volume decorrelation depends on the vertical reflectivity functions by means of a very well-known and relatively easy to implement equation. And now, if you measure volume decorrelation, we will see that if you have a model for the vertical reflectivity function, then you can start to estimate parameters about the vertical reflectivity function. And I was mentioning before that forest height is a parameter which is, you see, you need to make many things wrong not to get a forest height. But in general, what we mean here for forest height, of course, the volume that you see depends on how much you penetrate. So in this sense, for us, this forest height is just a visible forest height. So it depends on how much you penetrate. And for us, the forest height, as we call it here, it's the height difference between the point in which you have maximum penetration and the top of your canopy. Then, if you penetrate until the ground, then of course it's indeed a forest height which is comparable to what you would measure from the ground itself. So, and we understand, you see here, forest height is here in this small point here in this equation. And then you understand that if you like to estimate this parameter, what you need, first of all, to get the volumetric decorrelation. So this means if you have temporal decorrelation, you need to be able to compensate for it. That's the one. The second one, you need a parameterization for the vertical reflectivity function. So, or someone tells you, it gives you a profile, it gives you a shape. That's the one possibility. And one possibility is to use tomography. So this you had it at the beginning of the week. You use tomography, you get a profile. If you like, you can take this profile and use it here. Or if you don't have tomography, so you don't have a profile, you need to parameterize the function. And therefore, in this parameterization here, you will need also to invert for these structural parameters. And now this comes the challenging part, because you need a small number of parameters, because otherwise you are not able to invert from your data. That's the one. But on the other one, they should be representative enough so that you can indeed describe your data. So, and let's see what we can do. So, about modeling, how do we model this vertical reflectivity function? For modeling the vertical reflectivity function, we start from a simple consideration. You penetrate until the ground, in the best case, so you have two layers. The one is the ground, and the other one is the volume on top of it. Now, you assume further that ground and volume in terms of scattering, they are independent. So this means that the vertical reflectivity function, you decompose it between a reflectivity function that represents the ground. You like to be simple. You take a Dirac delta, nothing else. So the only parameter that you need to know is the ground topography, nothing else. And then you have a volume only, so without ground, reflectivity function. And that's the part that you need to parameterize. Now what you can do, you can take this part here, all this this decomposition into these two components here. You put it in the integral, in the Fourier integral, and you get a expression for the volume decorrelation like this. So now you see that you have a complex exponential where you have here the ground. This depends on the ground height, on the topography. And then you have here the volume decorrelation, so the volume only without the ground. And then you have a parameter which is called the ground to volume ratio. So this basically accounts for the difference of scattering powers between the ground and the volume. So it's just a ratio between these two scattering powers. So, and you see, it's a rather compact equation. It also has a number of interesting algebraic properties. But this is not the focus for today. What is important to know is that already this simple model has a number of parameters. So what you can do, let's say so, topography is unknown, and it's one parameter. So where it is? Here, phi 0. The height is unknown, and it's another parameter. So you're already at 2. The ground to volume ratio is an unknown. But now here it depends on how many polarizations you have. Because the ground to volume ratio, so the backscattering of the ground, depends on the polarization. We saw it before. So you change polarization, you have a more or less strong ground. So 3 polarization, you are already at 3 ground to volume ratios. And then you had the other one, you have a 5 parameters. So then what happens? And then you have the vertical reflectivity function of the volume only. This will depend on a number of parameters. And now you see that if you already with one polarization, you have 3 plus n unknown parameters, where n is the number of parameters with which you, you model the volume only vertical reflectivity function. So this is for one polarization. In one polarization, you measure one coherence. How many independent numbers you have in one coherence? A coherence is a complex number. How many real numbers? 2. Because you have an amplitude and a phase. So you measure 2 numbers, and you have to invert 3 plus n numbers. You say, it's already, the model is undetermined. So you can still invert and try to do something, but of course the solution is ambiguous. Or you need to guess something. You need to make assumptions. So, and of course, everything without taking into account the temporal decorrelation. Otherwise, this is an additional parameters. So, what we can do? We can now start to play some games. So, of course, we can start now to model also the variability of the vertical reflectivity profile of the volume only across the polarization channels. And we say the random volume assumption says that the vertical reflectivity profile of the volume only does not change with polarization. So at least this is something that it's out of it. Then at this point, the only thing that varies with the polarization is the ground to volume ratio. So you have, what do you have? You have topography, you have height, and then you have a ground to volume ratio per polarization. Now, 3 polarimetric channels, 3 ground to volume ratio, you are already at 5 unknown parameters. You have 5 unknown parameters, 3 polarimetric channels, 3 interferometric coherences. Each interferometric coherence is how many numbers? 2 numbers. So 2 times 3 makes 6. So you measure 6 numbers, and you have at least 5 unknowns. So now if you would like to have a determined inversion problem, you have 1 parameter available. So in this, you understand, this 1 parameter is the only parameters that you can spend to model the vertical reflectivity function of your volume. So therefore, many times what is done is just to express the reflectivity function of the volume as an exponential. So you say that you have a homogeneous distribution of scatterers from the ground to the top, then the radar wave propagates. While it propagates, it attenuates. So the only parameter that you need to know of the volume-only reflectivity function is just the constant of attenuation. Now you have 6 unknowns and 6 measurements. So at this point, the problem is determined. Of course, the fact that it's determined, so you can start now to invert for these parameters, but this doesn't mean that your inversion is not ambiguous. It could still be ambiguous. And if you like to survive, you need to regularize a bit your inversion. So you can regularize making assumptions, or there is also another game that you can make. So you can start to exploit your polarization a bit better. So you can start now to optimize polarization channels so that in one channel you don't have the ground. So all the ground parameters, they go away. So you don't have any more ground to volume ratios. So you have the one coherence, and in the one coherence you get height and extinction. So this is a bit the game that you need to make. Now the question is, of course, so you understand that a uniform distribution of scatterers from the ground to the top of the volume, it's a tree that doesn't exist in nature. So this is unrealistic by itself. And now the question is, how good is this then to invert, for instance, forest height? I don't care about all the other parameters because maybe for structure they are not representative enough, but how good can I get height? Therefore, there is a number of experiments that were carried out in the last, 15 to 20 years, and demonstrate that indeed, even with this very simple model, you get a good forest height. So, an example, Traunstein forest, so the one that we were having the profiles before. So, Traunstein forest, south of Germany, you see here we have also height measurements. So, the height basically varies between very short stands up to 50-meter tall stands. Then we apply this Polinsar inversion with this very simplified model for the volume reflectivity. That's the height that we get. So you see spatially, you can say looks reasonable, so there are no apparent artifacts, but of course you need to validate this. So we compare it with the LiDAR data, and you see in these points with the LiDAR data, this is what we get. LiDAR data here on the horizontal axis, radar estimated heights on the vertical axis. These are L-band data, and you get basically a nice correspondence between what you invert and what you actually have on ground. But I think the most important fact is that you are sensitive. Independently of the root mean square error, you have two facts. The first one is that you are not biased, and the second one is that you are sensitive to the whole range of heights from the smaller heights to the taller ones. Of course, this is because I just anticipate something. Your baseline is also quite optimized for this inversion. The question is, how reliable is this inversion? If, for instance, you like to see height changes. Now, this was an inversion, a forest height inversion of 2003. We did the same with an acquisition of 2008, 5 years after. So what changes do you see? There is one big one. Someone that tell me the change.
This clearing of trees inside.
Here you mean? Indeed. This is not the clearing, and this is not because the inversion was not sensitive. This was indeed the year before this acquisition, there was a storm that basically was throwing down all the trees here. So there was this big opening. So this is consistent with all the rest. Some other change. How does it look here? Height. Greener, closer to green, or closer to red with respect to this one? It looks greener. So at the beginning we thought it was a bias. It was not a bias. This is management. This is forest management. So This is a managed forest. This means that the people who take care of this forest goes there and cut the taller trees because they like to keep a homogeneous level of biomass for some reasons. And indeed, so the fact that they were cutting these trees is reflected also in this map of 5 years after. And somewhere else, if you look closely, you see also some stands which were smaller here. They grew up, and therefore you have higher heights. So of course, you see these changes with a certain accuracy. So it's not perfect, but the inversion that you make with interferometry, polarimetry, and even this simplified model tells you something that it's realistic. So you can follow not only the spatial dynamics, but also the temporal one. Good. Now, this is of course, it's an airborne acquisition. It's small scale. So we speak about acquisitions which cover, I don't know, 3-4 kilometers by 10 kilometers. What if we like to make something large scale? To make something large scale, we had this experiment with tandem-mix data. So tandem-mix is a system that gives you interferometry everywhere, systematic, single pass. So there you don't have temporal decorrelation, you have only volume. So this means if you are able to compensate all the system decorrelation effects, you access directly volume decorrelation, and I will show you now that with simple hypothesis, you can get height also from just one coherence without polarimetry. Let's see. So this is what we get. Now, single pole, we said. Single pole, now this is a disaster because we already have 4 unknown parameters. So you have the height, the topography, 1 ground to volume ratio, and we said even with the most simple and wrong hypothesis about the volume, you get 1 parameter that you need to estimate. So this means 4 parameters in total. You measure with tandem-mix. Normally, you measure 1 coherence in HH. So 1 complex coherence means how many real numbers? 2 real numbers. So you see, you have 2 numbers here, 4 numbers that you need to know. Too much. Let's start to make hypotheses. So what do we kill? Temporal decorrelation. Tandem-mix, single pass, no temporal decorrelation. What do we kill next? What would you kill? Let's put it like this. So it's X-band. Maybe you don't penetrate too much. What do you kill in this model here? You remove the ground. So this means you can still penetrate at the ground. You can still make the assumption that you penetrate until the ground, but the attenuation is such that you don't have ground backscattering in your data. So you have no ground layer here, no ground to volume ratio, no parameter here, and now you have the volume height, unknowns. You have the volume height, the topography, and then 1 parameter for the structure. How to go ahead? So now you have 3 parameters that you need to estimate and 2 measurements. What the next thing that you can assume? Many times, not always, but many times. Flat topography, correct. If your topography is flat over a scene, then this is just 1 phase shift. And if you know somewhere, you just need 1 point to know where your topography is, you know what the phase is, and then with 1 phase in 1 pixel, you compensate it everywhere. Where is 1 case where this works? Mangroves. Because mangroves, they grow on water. If they grow on water, the bottom of the volume, it's flat by definition, it's just the water. So this means you need to find 1 point on the water in which you can measure your interferometric phase. But someone said before that water decorrelates. So what can you do? You look for dihedrals, because somewhere here on the border of these mangroves, there will be dihedrals. So you will have the reflection from the trunk of the mangroves to the water. This is something relatively stable. So from this dihedral, from this point where you have the dihedral, you have a very clean you have a high coherence, you have a very clean phase measurement, and you subtract the phase there from everything else. And this was an experiment done by colleagues at NASA. They took around 20 tandemic scenes in this mangroves area between India and Bangladesh, and they were able, without too much effort, to get this forest height. And still they were using complex data. So with this one phase, they were compensating the topography, and therefore they were still having an amplitude and phase measurement to get forest height and one structural parameter, so this exponential, this attenuation. So how good is this map? It's good enough. You see you have a root mean square error which is in the order of 1 meter. Maybe here it's a bit optimistic, so it's not the same everywhere, but this is something with, you know, even with just a simple modeling, this is something that you can get. However, if you don't have a flat topography, then you don't know topography. And then what can you do? Well, if you don't know topography, let's say so, this is one of the problems. The other problem is about reflectivity. So, and for reflectivity, you can parameterize it. If you cannot parameterize it, then someone has to tell you a profile. And then you make another assumption. The other assumption is that the X-band reflectivity is not too far away from a LiDAR reflectivity. And why we speak about a LiDAR reflectivity? Because in this case we have JEDI. JEDI is a LiDAR which is deployed on the International Space Station. So it's active since 2019, and since then is acquiring waveforms everywhere. Of course, it's a LiDAR, so you don't have everywhere a waveform, but it's just a sampling the Earth's surface. But every time that you get a sample, you get a profile. And now, with a bit of you know, with a bit of fantasy, you can still say this profile is representative enough for my tandem mix vertical reflectivity function. So, and therefore at this point, you parameterize just in one shot, you parameterize the vertical reflectivity function in this equation. It's true that you don't know the topography, but then you just take the absolute value of it. If you take the absolute value of it, the topography goes away. Therefore, you parameterize the topography, you parameterize the vertical reflectivity function, and the only unknown is here the height. And again, so with the reflectivity function, you can describe the relationship between height and coherence. We will see this in the exercise today, and you will implement it actually. And then from here, you can invert height. The same game. So just to show you how good it is. So we are here where? This is somewhere in Gabon. So you have this a longitude, a few degrees in longitude, and around 1 degree in latitude. So, and you see this is the situation how JEDI samples. Well, this is actually an old picture, but it's not has not changed very much from here. But this is how JEDI samples the surface. So you see between, there can be several kilometers between one footprint and the next. So this means you have somehow to parameterize now your tandem mix coherence, knowing that you may not have one footprint, so one JEDI profile for every tandem mix pixel. So and therefore you need somehow to bridge this sampling difference. Again, a bit of fantasy. What you can do, you know, we try to do something like this. So we take all the footprints in one tandem mix sense. So we take all the profiles, we put all the profiles together, then we make like a matrix, making a matrix. Again, we make an eigenvalue, eigenvector decomposition. It's a sort of principal component analysis. So you find among all these profiles, you find a set of profiles, and all of them are less than, let's say so, you have the first profile, which is the one that is most representative for all the profiles here. We call it sort of mean profile, and then to this mean profile you can add more and more component, and you can become more and more accurate in getting the LiDAR profiles. So here we don't care, we just take the first one, and then with this we parameterize basically this relationship here. And therefore we define a relationship that tells you so how the coherence change as a function of height for a certain capacitor, of course. So this is what we did here, and that's the result. So that's now something a bit larger in space, the JDI waveforms, tandem mix DEM, you see you have a lot of topography, tandem mix coherences, so there are several acquisitions here, I don't remember how many, but this is the tandem mix coherence at 25-meter resolution, you see it changes a lot, you even have some topographic effects in the coherence. But then with this game, so we get the mean profile, with the mean profile we get a height. And this is where you started with JEDI, and this is when you end up with tandem mix using the JEDI information. So you fill up the space between the JEDI, you fill up the space between the JEDI height information, and therefore you get now a continuous map. How good it is? You know, for what you could do in this case, it's pretty good. It's basic, it's almost unbiased. There is a bit of standard deviation. The standard deviation depends on many factors. It depends primarily on the fact that, of course, you are trying to invert height with just one number and just one profile. So it's true that if you change scene, you adapt the relationship between coherence and height, thanks to changing profile. But of course, then you try to invert height only with one profile and all the rest of the pixels. So this gives you, of course, some uncertainty. The second source of uncertainty is that, of course, there is a geolocation error in the JEDI footprints, and therefore this brings you some standard deviation when you make this sort of comparison. And then, of course, you know, it's I would say that in general, the rest of standard deviation is just because, as I said before, even if you had the correct profile information here, you are inverting height only from one number. So, you know, you cannot ask too much, at least in terms of accuracy. But the fact that you use the right profile gives you something which is nearly unbiased. So, more and more large scale, Amazon. So now here, it's around how many degrees? This is many degrees actually in longitude, many degrees in latitude. And you see this is a composition of more than 12,000 tandem mix scenes. This is the coherence. You see you have very high coherence, but of course you have areas where this coherence is higher, areas where the coherence is lower, but then the coherence can also change. You see here, you see that this is basically the acquisition pattern of tandem mix. You find the orbits there, basically. And this depends because if you change the orbit, you change also incidence angle. And if you change incidence angle, you change slightly the capacitor. If you change the capacitor, of course, also the coherence can change. JEDI. JEDI looks like this here. The sampling is a bit better, but this doesn't change the fact that between one footprint and the next you may have a kilometer. And you see here, you can go forth and back, and you see, I know I'm making you crazy, but you see here that, for instance, where the height is very small, principle where everything is blue, then also your coherence is higher. Where the height increases, your coherence becomes closer to darker intensities. And this is what you like to expect. So therefore we apply the same game. So for every one of these tandem mix scenes, you get a mean profile from the JEDI footprints, and then you use this mean profile to get back the height. The result is this. So you see that it basically, it's consistent with the JEDI information. So here there is still no, so this is just what you get from tandem mix. So there is no anything else. So of course you can still try to use the tandem mix heights to somehow try to compensate for biases, but even without doing this, you get something of this kind, which is still consistent. And then you see here, again, this is a comparison between the J-die heights and the tandem X heights. You have at least on this large scale, you have no relevant biases, and I think the standard deviation is in line with what you would expect. Of course, this doesn't change the fact that you don't have biases at large scale, doesn't change the fact that you may have biases at smaller scales. And for instance, you see it here, you can see somewhere also the radar strips still. And that's because basically, in that case, tandem X was always on the same orbit, but just changing the incidence angle. So this means you change the capacita, but you basically invert with a similar profile. So between one orbit and the next of tandem X, you have a change of capacita, so your relationship between coherence and height change, but the change of mean profile is not as large. So this means that this game of having just one mean profile per scene, of course, finds here its limitation. But what you can do, as I said before, you can still take the J-die heights and try to compensate residual biases in some way. Good. Maybe questions before saying 2 words about agriculture? Yes?
Yeah, just curiosity, how much resources would it take to do such a large computation over the Amazon?
Resources, you mean hardware, software, this sort of stuff. It takes a bit. So I think, let's say so, to calculate all this, to invert for height for one scene, it's not long. So this you can do it, it's minutes. What takes more is, of course, to get all the data from the tandem X archive. So it is especially time. Then for the rest, of course, this is 12,000 scenes. What we were doing, we were taking the scenes as they are and then downsampling. And then with this, we could reduce a bit the space, but it takes quite a lot of time. So already so by processing this in a multi-thread and whatever, it was taking, I don't know, to get this, it takes a few weeks in total, approximately. But with biomass, you will be able to do this, of course, too, in different ways. But agriculture, I said before, what we said for forest, you can apply for agriculture, but agricultural volumes, they are a bit special. So, because when it comes, for instance, so what are the difference between agricultural and forest volumes? So the first one is that, you remember, one of the assumptions that we did, which for forest it's normally verified, is this random volume assumption. So the fact that all the vegetation elements, they are all distributed in a random way, so that the vertical reflectivity profile is the same for every polarization. With agriculture, this may not be true. It depends on the frequency, it depends on the plant, but the fact that normally you have these elongated stems, and they are all vertical and all compact to each other, this can make that in some cases this assumption is not valid anymore. So you don't have a random volume over ground, but you have an oriented volume over ground. So this means polarimetry is fine. So you need polarimetry to invert your model, but you need also baselines. The vegetation layer is shorter. So if the vegetation layer is shorter, you tend to penetrate more. Surprisingly, you penetrate a lot also at X-band. You have quite a strong ground contribution at X-band. So you have to be careful when you try to regularize your problem by separating ground and volume, because you still have maybe, you think that you have only volume, but you may have still a strong ground. And, but you also need some larger baselines, because your capacita must be adaptive, so must be sensitive to these shorter volumes. And if you like to see, how to say, if you like to acquire interferometry in repeat pass, you need very short temporal baselines because agricultural crops, they grow fast. So 3 days might be a long time depending on which point in the phenological cycle you are. So in this case, of course, single pass acquisitions, they are always preferable. And the modeling now starts to be difficult because maybe thinking that you have just an attenuation factor to model your vertical reflectivity function, this is maybe not enough, so you need to spend maybe more parameters. Anyway, so here you see an example. So it was a campaign in 2000 and something, 2014 or 2015, where we were sampling in time different fields. And then, for instance, this is an example for inverting height. In this case, we applied this concept of having an oriented volume. And we were using not one baseline, but different baselines. And there, all the equations were derived for this particular case. And you see here, if you start to invert for height, you see a signature. You see that your plot, your crop is growing. This is what? This is width. So this is growing. At some point, however, you don't see a lot anymore. So it looks like it's getting shorter. The thing is that what's happening is just it's getting drier. So it's getting drier, and therefore you see a smaller volume. So, but in general, the height that you estimate basically follows also your ground measurements. What is interesting to see is also this part here. You see that now it looks like you start to have holes in your field. This is not an artifact of the estimation process. It's just because you have situations like this. Basically, the plant start to die, or for some reason, because of also you know, you get a storm or whatever, they just basically on the ground, and therefore you see you are sensitive also to this sort of stuff. Then for corn, you have an evolution which is a lot, of course, they grow a lot more, up to 3 meters, and again, even in this way, you can follow this development. So somehow you see that you have this Polarimetric frameworks allows you to, as I was telling you at the beginning, it's something that making the right assumptions, you can apply it also to different volumes. Frequency effects. So we spoke a lot about frequencies, and I think the most important frequency effect is the fact that, so if you change frequency, you change the propagation of the wave, first of all. Therefore, your wave becomes, so if you increase the frequency, the electromagnetic waves are more and more attenuated through the volume, so you penetrate less. Then what happens? It happens that if you increase the frequency, you decrease the wavelength, so you are more and more sensitive to scatterers which are smaller. So, for instance, I don't know, at L-band, you are sensitive to the trunks, to the stems, not really to the leaves. But then if you go to P-band, at P-band, of course, the ground becomes a lot stronger because you penetrate a lot more. But you are sensitive also to these larger elements, so more to the grounds and to the larger stems, so to the larger to the larger branches and so on. And then if you go at X-band, you have the opposite situation. This we commented also before. Now maybe you don't have a lot of ground here, so at these points this modeling is fine, but then you get also sensitive also to these very small vegetation elements. Now you may see it, of course, as a so you see that getting information about forest structure, it's not a single frequency problem, but it's intrinsically a multi-frequency one. And what one frequency doesn't see, then it will be seen by a different frequency. Still, we don't know how to relate the different frequencies, and the main reason for it is because there are no models that allows you to relate vertical reflectivity functions at different frequency with the right accuracy and for the largest possible frequency intervals. But still, it's understood that the more frequency you have, the better your characterization will be. And this is something we already commented. So then, another important point about non-volumetric decorrelation effects. So now we start here, these slides will start to become very full. So we started from here. So this is the coherence that you measure, and you estimate it from the data. We said you factorize this coherence in 3 factors. So now here you see that they are called a bit different, because this is with respect to before. The one of before was already simplified in the most, in the most important ones. Now here we try to put all of them. So you have one which is about propagation, one is about scattering, and the other one is about your ability to process the data, to collect and to process the data. So scattering. In the scattering you have at least you can factorize it in 2 contributions. You have the temporal decorrelation, and you have basically the coherence that changes with the baseline. So you can make your baseline smaller and larger, and this coherence will become larger or smaller. So, and here you have several contributions. You have Doppler decorrelation, range decorrelation, not so important to know what they are, but of course they can become more or less dominant depending on the system characteristics. But what is important is that in these decorrelation terms that depends with the baseline, this is where you have the volumetric decorrelation. So in principle, once you isolate this term, then you have still to make sure that you compensate for it. And especially in the biomass case, we will see this afternoon, there is one term which is important, is gamma range. So this is a decorrelation that depends from the fact that your resolution is so large that by changing position, you already see different portion of your reflectivity spectrum. And this causes a decorrelation. And this is a decorrelation that, so it depends just from a change of viewing angle, but it doesn't depend on the volume that you have. But it's very strong for surfaces, because for surfaces you would expect to have a coherence equal to 1. So there, just with this decorrelation factor you already decrease. For volumes, it will not be so strong, the effects. But of course, if you like to invert parameters, you need to have it under control. Then propagation. Propagation, you have atmospheric, you propagate through the atmosphere and to the ionosphere, and they can give you the correlation just because, for instance, they can delay the propagation, and this delay can also be azimuth dependent. So you have a number of effects, but in general, this you can compensate. With biomass, of course, they are strong, maybe also a bit stronger than what we expected, but we are learning how to deal with them, and I think it's already today we can compensate many of them. Then system and processing. Here we were listing at least 8 terms. So basically whatever it depends on the system, whatever it depends on your ability, for instance, to make when you make interferometry, you need to co-register the images. You need to compensate a number of things. And you see, all of them, they can also be quantified. At the end of the day, however, you say that this system and processing decorrelation, you approximate it with one number. And this is many times is enough. But the message of this slide is that in principle, you can, so you like to arrive here at the gamma volume. And the gamma volume is hidden here. So before arriving to the green part, you have to compensate for this 2. And then compensating for this 2 is relatively easy. This is something that you can control. It's something that you can know with a certain accuracy, but you can know and you can control and you can compensate. When you arrive to the green part, that's painful, because you have now here, this you can still compensate for it, but then gamma temp, the temporal decorrelation, that's the part that it's more difficult to know about. And in general, you don't know anything about it. And this is something that you must be able to deal with it in your inversion. So let's see, how strong is temporal decorrelation? So how much do the scatterer on ground change in time? So it's the same forest, so structure, the forest structure is not changing, but it's just the scattering is changing with time. So same image of before, at p-band. Volume decorrelation. So basically here I think it says 24 hours. You can get a forest height map. In 24 hours you don't have a strong change. You make a height map, this height map is reasonable. You can validate for it. Sorry, you can validate and you will find that this is consistent with, for instance, a LiDAR measurements. So for instance, a p-band, 24 hours is not bad. Now, no, sorry, I got mistaken. No, this is a volume, this is 10 minutes. 24 hours is this one. My bad. 24 hours. SAR phases, they are still there, most of them. The volume, they start to change. What can happen in 24 hours? It could be raining between one day and the other. So if it rains, you change the electric properties of your forest. What else can change? Fire. That's a very unlucky case, but of course it can change, yes. But in this case, there was no fire. You may have different wind conditions. Of course, wind can destroy your coherence even in 10 minutes. If the wind is very strong, then, and you are not at p-band, but you are maybe already L-band or C-band, then already 10 minutes can be a long time. So you have all these factors, and all of them, they have a different temporal decorrelation with a different model, and of course this complicates your inversion. But in this case, if you go to invert forest height without taking into account the presence of temporal decorrelation, then this is what you get. You are biased. You are essentially biased. It's not a problem of adding a standard deviation, of being inaccurate. It's just that, so the smaller stands, they become taller. Because it's a temporal decorrelation, if you don't model it, it's misinterpreted as a volume decorrelation. You remember, for the same capacita, if your coherence goes down, then you interpret it that the height goes up. And now here you have a coherence that is going down, but this is time. It's not geometry, it's not volume, but you misinterpret it. So you interpret this time for a baseline. And therefore, that's why you estimate your stands here become taller. Of course, the effects, it's a lot stronger on the shorter stands. We will see this afternoon. But look at this. For instance, take this surface. This is basically surface and very short trees. And here you have trees which are 40 meters. You interpret them as trees which are 40 meters tall. So that's a dramatic effect. Now, of course, you can make the same experiment. The one before was p-band, I think. Now you can make the same experiment at L-band. And now you start to have months. And you see that after 2 months, you have no coherence anymore. So somehow, if you like to make parameter inversion at L-band, or you know, with this repeat pass configuration, you have to ensure a certain revisit time. But still you see that even after 1 month, the coherence is not gone. There is still coherence. So, but this is for me, it has a consequence. The consequence is the following. So temporal decorrelation does not destroy your inversion. So if you like to be sensitive to structural parameters, you must have a baseline. If you don't have a baseline, then you don't have sensitivity to structural parameters. Temporal decorrelation can make the inversion inaccurate. So therefore, this is where you need to take into account. So it's a modeling problem. But having just time and no baseline, so that's a problem that you have an observation space which is not sensitive. So your modeling becomes more difficult. Well, p-band, now here you see that it's a lot more stable in time, and then you see this is 2 months. Now you think to the biomass mission, you have acquisitions every 3 days, and indeed this is what we saw, is that the coherence is stable, but we have a lot of coherence variability because of rain effects, and you have this change of the electric properties on ground, and still you have some decorrelation, which still up today it's not completely modeled. But another effect which is also important to say is that the coherence is not, if you have this repeat pass configuration and you change the revisit pass, you can make it from smaller to larger, the temporal decorrelation is not, how to say, uniformly going down. Let's see an example. So let's say so, Traunstein forest, single baseline, Pauline-SAR inversion, 10 minutes repeat pass, basically L-band, negligible temporal decorrelation, forest at inversion, something like this, it's fine, acceptable. One day, so in one day you start to have all these changes. So you have a temporal decorrelation that you cannot ignore anymore, but you don't put it in the inversion. That's the inversion bias that you get. Not so strong somewhere, but somewhere else very strong. 5 days. Look at this. Distance here. Are they more similar to this or to this? I think if you look at a mean level, they are more similar to this than to this. So your bias is going down. Why? Because here you were getting back your coherence. So your forest, in terms of the dielectric properties, after these 5 days was closer to this acquisition than to this, independently of the time. Of course, after 7 days, this was the situation. Now here you get a bit worse. After 13 days, so all this bias here somehow was disappearing here. Somewhere else there was a stronger bias. Here you lose all these short stands. So you see that this temporal decorrelation, as I said, is a non-stationary phenomenon. So it can be there, but also cannot. And sometimes if you have this time series, even if you lose it one day, you may have it, even if you lose coherence with 2 acquisitions, you may wait for the next acquisition and you may get your coherence back. So having this possibility of having some sort of revisit, then of course increases, but every time having a baseline, then this increases also your possibility to have some inversion. Good. Then maybe the last step, let's see how far we can go. So, but so up to now we were trying to reconstruct height. Now we like to reconstruct the vertical reflectivity function. There was a question before, how do I get vertical reflectivity function? And the one way is with tomography. You spend time and system resources to get many acquisitions, and with the many acquisitions you basically sample this coherence for different capacitas. Then you have many capacita, you have many of these samples, you invert this Fourier transform. And there you get your reflectivity function. Now let's suppose that you have, in the limit, of course, still one baseline, or if you are a bit better, you have 2 baselines. What can you do? Of course, if you have these 2 baselines, you don't have anymore the chance to sample capacitas. So with 2 baselines, you have 2 coherence. You can also start to optimize polarizations so that maybe with these 2 coherence, you have a better guess of your reflectivity function. This is fine. But in general, just inverting this Fourier relationship start to find its limit. But you can do, still with modeling, you can do something of this kind. So you take your vertical reflectivity function, whatever it is, and you express it as a combination of many functions. You express it on a function basis. Then it's a linear combination of functions, something like this. And now you have to take this linear combination here, your f of z here, and you put it in this equation, and now you have, in principle, for every coherence that you measure, you see that this coherence that you measure, it's a linear combination of basic coherence, of Lego stones. And now you have to play with the Lego stones so that you need to know how many of these Lego stones you need. So let's say, so, or if you like, so you have here, so you have the green Lego stone, these come by default. And then you can now, if you have one baseline, you have two numbers. With two numbers, you can measure back two coefficients. So and now you have to find out what's the weight of these two coefficients with respect to this. So as always, you play with this, your inversion problem must be determined. If you have then, so this is with one baseline, you can arrive up to here. With two baselines, you can arrive up to here. So when you see, every time that you have one baseline more, you have two functions more. So your characterization becomes more and more accurate. But the interesting fact is that playing like this, reconstructing the vertical reflectivity function, on the one end, is just a matter of estimating a few coefficients. So it's a linear system of equations. So it's a system of linear equations. So, and this is something that you can resolve easily. The other fact is that you have an inversion, but this inversion is somehow constrained. Of course, the challenge is to find the basis which is most representative for the data that you have, for the forest that you have. So, because of course, if you know any, if it's not representative, so then what you reconstruct is biased. So. Now, at the beginning, it was proposed to use these Legendre polynomials. It's, I would say, you know, it can work, but it doesn't necessarily give you the best reconstruction. What you can do, you can also, for instance, derive a basis from data. Suppose that you have a tomographic set. From this tomographic set, you derive your tomographic profiles with just imaging. So there you make no assumptions on anything. Then once you have your basis, then you can derive this basis in many ways. So and what we do normally, we try to have functions which are orthogonal to each other. So because then with the lowest number of functions, you get the best representation. And then once you have this basis, you can apply then to other data of the same kind. Think about biomass. Again, biomass is the examples that allows you to make many things. So in biomass, you have the tomographic phase at the beginning. So so sooner or later, there will be a database of profiles everywhere in the world. And now you take these profiles, make a basis, and use this basis, and you can, you know, you have all the degrees of freedom that you like. You can also have this derivation of the basis per geographic area, whatever. So, or per forest type, someone tells you, you know, some sort of preliminary type classification, and then from this, you can get from this you can get the basis adaptive in space. And then once you have this basis, then you start to enter in the next mission phases where you have all interferometry. You have dual baselines, or at least for how the mission looks like now. You will have a dual baseline acquisition. So you have interferometry, and then you can start to apply the basis that you got in the previous phase in the next phase. So every year you have a profile. Of course, it's a representation of this profile. It's in a low-dimensional subspace, but still it's a profile. And then you can start to think, maybe to see changes, structural changes, dielectric changes, whatever. So you see, it's a very simple concept, but with a low number of acquisitions and an appropriate choice of basis allows you to make many things. So this, of course, was applied at the beginning in simulated data. So this is a case, for instance, where you have a uniform volume, and you know, if you apply to data simulated from this uniform volume, you get indeed the representation that you expect. You can also have a volume which is more concentrated to the top, and again you are able to get this. And in principle, you can even start to discriminate this sort of volume from this sort of volume. As I said, it's a low resolution, if you like, representation, but still, it tells you something. Then this was also applied to real data, dual baseline acquisition, same Traunstein forest, and then here just with a dual baseline, so this means 4 functions in total, and these were the profiles that we were obtaining in HH and in HV, so this is not only a theoretical, but they are all the same polarization, it's HV, but 2 different lines. So you see, this is a concept that works also in practice. Of course, to make it work, you need, as a preliminary information, the ground topography and the top of the volume. So you need somehow to constrain the volume, and then there you can invert the height. So maybe, so we have 10 minutes, and then maybe just to complete the overview. So now you have profiles. That's maybe an important thing. So we were speaking before about temporal variation, and this tells you also, then makes the link also to your temporal decorrelation. So basically the temporal decorrelation express how much this underlying reflectivity function changes. And even for the same forest, for the same geometry, this reflectivity function can change a lot. For instance, now these are profiles obtained with tomography. So it was a data set. There were 5 tracks. There are not many. Vertical resolution around between 15 and 20 meters. Not very large, but still you can do something, at least in distance, which are around between 30 and 40 meters. Now, this was one day after a number of sunny days, so in summer, so your forest was in a equilibrium, so rather dry, with a certain water content. You see here, you penetrate and you see the ground. From HH, in VV the ground becomes weaker because now you lose the dihedrals, and then in HV you got, of course, a much attenuated ground. Now, so this was one day. 2 days after, we had a second acquisition. In between, there was a heavy rainfall. So the forest was wet. What do we expect here? After the rain, you see more ground, less ground? You see less ground because the water is higher and the attenuation is higher. So the water content is larger and also the attenuation is larger. That's indeed the case. So you see here, your ground your ground here is weaker, and that was the gap that I was telling you before. Look, it looks like here, the reflectivity is going down. It's not clear if you have a gap in the forest or your forest is drier. Here you have the answer. The forest is drier. So indeed, after the rainfall, you see now that all these components here, they become visible just because of the electrics. So in principle, this tells you also that reflectivity, or even reflectivity from tomographic profiles, is a liar. So never believe it. Somehow you have this underlying ambiguity that reflectivity depends on many quantities. So even for the same frequency, it depends on the incidence angle, depending if you look more steeper or more shallower, but it depends, most importantly, on the dielectric properties. You change the electric properties, you change the reflectivity profile. It depends also on the season, because look, this is what you have in spring, and this is what you have in autumn. In autumn, now, in spring, you have transpiration through the leaves. So you don't see the leaves, but you see the transpiration. So you see here a different water content than here. So here you have a lot more water. Here you have less water because it's not transpirating anymore, and therefore also your profile change. And being able of understanding this variability it's the step that you need then to use these profiles to characterize a bit better your forest. And in particular, it comes to the characterization of forest structure, where there you don't like to see the electrics, but you like to see the geometric distribution in 3D of the scatterers. And the idea was, let's not use reflectivity, but let's use the position of the peaks. But let's see it. So we started from simulated data. So you have a young forest. In a young forest, you see something, it's more or less some homogeneity, if you like, but short trees. You can simulate reflectivity. We took just a simple model and we simulated the reflectivity. We took a transect somewhere, and you see that along this transect, all the profiles, they look the same. They're very homogeneous. You have basically almost no gaps. And then what we did to try to interpret this, of course, one profile only doesn't tell you anything about the structure below. One profile is ambiguous. But what you can try to do, you can start to see the variability of nearby profiles and to see how they change. So this means, for instance, so we took, I don't know, for every profile, you can get any profiles at a 20 by 20 or 25 by 25 meter resolution. This is because you need to estimate the coherence to get the profile. So you need a multi-look cell. And then you start to evaluate the variability of this profile, of these profiles in 100 by 100 meters. So it's a bit of statistics in the end. And then here, for instance, between the white line and the consecutive white lines, you take all the profiles in this, and you get a plot of this kind. All the profiles, they look the same. Not, you don't have a lot of variability in vertical. You don't have a lot of variability horizontal. Then you take an old forest, something which is 500 years old, very developed. The situation here, it changes a lot. So you have a lot of, you can make the same game. You take squares of 100 by 100 meters, 1 hectare, and then you see how your profile change. And then in these changing profiles, you see now that the profiles, they change a lot vertically, they change a lot horizontally. And therefore you understand this is a very, it's a very heterogeneous forest. Then you take an old forest like this, but after a fire event, and the fire event was burning patches. And in these patches, you see they reflect also in your profile. Now here, of course, you have also the understory somehow disappeared. You have some of the taller trees which are still there. But now here vertically, it's not very heterogeneous, but horizontally it's very heterogeneous because of the gaps, because of the fire. And then, after 200 years, same game. Now the tree starts to grow up again, and then when they grow, now you are in a situation which is closer to this, and therefore you start to recover these heterogeneous, these natural states with this heterogeneity, horizontal and vertical. What you can do, now you need to characterize this 3D structure. 3D means 3D, but of course you need a parameter that should take into account about all this, this 3D variation. What you can do, however, you can take the 3D structure and project it on the horizontal and vertical plane, and therefore you have two measurements and two indices. And basically the one express how heterogeneous is your forest in the horizontal direction. So in principle, how much does the profile varies from the one cell to the next, and how heterogeneous it's in the vertical direction. So in principle, how many peaks do you have here? And then you can represent the different stands in this sort of horizontal and vertical structure matrix. What you understand is that even if you take 3D structure and you boil it down to just two indices, then you have some discrimination, because you can discriminate, for instance, let's say so, different stands, they have different horizontal and vertical structure, and therefore, for instance, between this and this is easy to find out what is more heterogeneous. For instance, in this case, You just discriminate through the vertical structure, but not through the horizontal one. And between these two cases, vertically they look the same, but horizontally they are different. So still you have this ability. It works also on real data. We have several experiments. Here I like to show you now to close just an example in which I like to show you that this concept works also for seeing changes because, for instance, of management. Traunstein forest, you have areas which are just left grow as they are, and some of them they are managed. So this was the vertical structure, how it looked like in 2008. This is it's a map that it's obtained from tomographic profiles. After 4 years, you see vertical structure is increasing. So it's becoming more heterogeneous. So this is indeed reflects all the management practices. So in 2008, in many cases, you have a situation like this. So it's a mature and homogeneous forest dense where you have all these tall trees. But then, during the years, these tall trees are cut to allow lights to penetrate and to allow the smaller stems to grow. And therefore, because of this, you increase vertical structure. So you see these signatures, what you have in your data, they are actually something that corresponds to the reality. So good. So it was, I stop here, I finished my time, but I think you had already quite a wide view. Right? So what you can do with polarimetry, what you can do with interferometry, what happens, what changes from having or not having polarimetric channels, and still with the same polarimetric channels, what do you get if you have one baseline more or one baseline less?